Underground, there are some bacteria that feed on hydrogen and produce a very poisonous substance called hydrogen sulfide.
And what does that do?
It's very poisonous. It's like a small amount of hydrogen sulfide is fatal. So luckily for us in UAE, we are dealing with high pressures and temperatures that are hopefully unsuitable for bacterial growth. The other problem is hydrogen tend to cause embrittlement in metals. So when we inject underground in our wells that we already have, it can damage the wells, which can risk leakage. So we need to make sure that the design life of the well is not reliable if we are injecting hydrogen. It will reduce it significantly. So these are the risks with injecting it. But the benefit is that we don't have any contact with people, as hydrogen is very flammable. So we avoid this risk, and we avoid risk in the surface.
Welcome back to KU Pulse, the podcast. My name is Dr. Glenda El Gamal, and I'm a senior lecturer in the General Education Unit at Khalifa University. And I'm very excited today to have a success story from Khalifa University. He's a Khalifa alum, a graduate of Khalifa University, and he did his master's here at Khalifa. He is now an engineer and researcher at ADNOC, and his research specializes in hydrogen and carbon. Welcome, Ahmed.
Thank you. And thank you for your nice introduction. So I'm Ahmed Alzaabi, and today I have a really exciting topic to share. My research topic is hydrogen and carbon storage.
Hydrogen and carbon storage.
Yes.
Well, first of all, take us through, I believe this storage is underground, right?
Underground.
So first of all, let's inform the viewers about how these gases that you're researching, how they move underground, because that's the key, isn't it?
Yeah, it's the key. You're right. But I think it's better to first share the objective of why we actually do it.
Certainly.
Yeah. So the objective is all about renewable energy. So what is the problem with the renewable energy? It's intermittent. It's not continuous. In summer, we have abundant source of sunlight, solar energy. But in winter, the days are shorter and we have less sources of solar energy. So what we propose in this research is to gather as much renewable energy as possible, for example, during summer. And sometimes during summer, we can have a surplus of energy. Instead of wasting this energy, we can convert it into hydrogen. And during winter, when we have less supply of energy, we can use this hydrogen to compensate for this lack of energy. So this is the general idea where it started. And why hydrogen? Hydrogen is very clean. We can get it from electricity using electrolysis. And then we can store it and then use it whenever we need it. So it's like a seasonal usage of hydrogen. The other problem is, which is the bigger problem, how can we store it? It's a gas. It's very difficult to store gas and very costly to store gas on the surface. That's why, from our expertise in the oil and gas industry, we know that we have huge spaces underground that we can use to store hydrogen. So this is where it started.
Okay. So you're saying that it's subsurface storage, right?
Yes.
And I believe we have some special rock in the UAE
Yes.
where you can store it. So tell me, what's so special about this rock? What do you call it and why is it special?
It's carbonate. We have abundant carbonates underground. And we have a lot of experience with carbonate rocks. And we know that from our experience, we know that carbonate rocks have stored natural gas and oil for millions of years. So we know that when we store hydrogen in it, it will be safe. We will not worry about leak or any potential problems. There are, of course, other risks. We'll talk about them later. But we know they are reliable. We have a lot of information and data on them. And actually, I have a rock sample with me here today.
This is carbonate?
This is carbonate.
Okay.
And what we do, why we store it underground? So the rock, as you can see from this side, it has some void spaces. These void spaces are what we call pores, where we store the gases.
So it's like skin, it's porous.
Yes, exactly. I like to take analogy with a sponge.
A sponge, okay.
A sponge.
Right.
So it can store gases inside it, and then we can produce it. In the case of hydrogen, we can produce it at a later stage. But in case of CO2, because of we want to reduce greenhouse effect, we want to inject carbon dioxide underground, and we don't want to produce it. So this is the objectives are different for each gas. So actually, this rock sample, it doesn't have a lot of pore spaces because the highly porous rocks are actually very valuable. I couldn't break them. This is very, it has low porosity, so it's good for demonstration, but not for experiment.
So how can you see inside these rocks? I think you use some sort of special 3D imagery. Can you tell us about that?
Yes, certainly. So our method is actually similar to what they do in the medical or the medical industry. So they use X-ray to look into the bones inside the skin, right? So we do something similar. We take a small sample of this rock, we put it inside a sleeve. As you can see, this is actually what I have worked on. It's a very small sample. It's inside a sleeve, and then we have end pieces, and then we close it and we secure it with some aluminium, and we connect some flow lines to inject the gases inside.
And how can you see inside? What's happening?
Yeah,
You can see.
so we place it inside an X-ray imaging device. It's called microcity X-ray imaging. So it's inside, and then there's like an X-ray source and an X-ray receiver. And what we do is when we inject the gases, we take an image, and it will show us inside the rock what is happening. And typically in a normal settings, the rocks underground will be filled with salt water. We call it brine. So we replicate that. We inject salt water. We fill it with salt water before we inject the gas. And then you can ask me, how do you distinguish between the brine and the gas?
Well, how do you distinguish between the brine and the gas, Ahmed?
Yeah, it's actually because they have sometimes we will not be able to distinguish between them clearly. We tend to dope the brine. We make it heavier, and the X-ray will, when it scans, it will distinguish between the rock, the brine, and the gas by their density. So the gas will look black because it's low density. The brine will look white because it's doped, it's very dense, and the rock will look gray. So
Now, this is a very small sample of rock. You're dealing in a much bigger scale, aren't you, in the real world?
exactly,
Yes.
exactly. So what all the information we get from this small sample, we can extrapolate underground under huge formations, and then you can ask me how reliable it is.
Well, how reliable is it?
We always take samples when we drill underground, and we already have abundant of data, as I mentioned earlier, from underground. So if we have similar properties inside this rock, we can interpolate what we have learned from this small sample. And also we have, as I mentioned, we have several different samples. The limitation that we face, which is with carbonate especially, is that they are very heterogeneous. The properties are very different from each site. I mean, even when in this rock, if I take a small sample as this one from this sample, here it will be much different than here. And this is a problem when we do comparative studies with different gases. People tend to use different samples with different gases. The unique feature of this work is that I used the same rock sample for the different gases. So we eliminate the issue of different pore system, different properties of the rock.
Now, you mentioned you're dealing with hydrogen and you're dealing with carbon dioxide.
Yeah.
Can you compare their behavior and their movement?
Yes. And I also included nitrogen.
Now, why did you use nitrogen? There's a special role for nitrogen, isn't there?
Yes, there is.
Okay, tell us all about that.
Yeah. So nitrogen is used as a benchmark. And many studies tend to work with nitrogen because they have limitation in injecting carbon dioxide and hydrogen. So I included it as a reference. And there is also another role that we can use hydrogen for, which is called a Cushing gas.
Cushing gas?
Cushing gas. So what does it mean is that before we inject hydrogen underground for storage, we inject nitrogen, and then we inject hydrogen above it. So why we do that? We do that to minimize the trapping of the gas underground. So because as I mentioned earlier, the underground is filled with brine, right? If we inject directly hydrogen, the hydrogen will concentrate above the brine. But with time, brine will tend to migrate slowly and then trap some of the hydrogen. Every hydrogen that is trapped is an energy loss. We want to minimize it. So we inject some amount of hydrogen, and then we inject some amount of nitrogen, and then we inject hydrogen above it. So that when brine will start to migrate and push the gas, it will trap some of the nitrogen, which is not valuable. It's air, but we will not. We will minimize the trapping of hydrogen. For sure, hydrogen will be trapped. The pore system, the rock systems are very complex. Trapping is inevitable, but we want to minimize it as much as possible. And to get back to your question, how carbon dioxide and hydrogen behave underground. It's very different. In the surface, we see that they're all gas. They behave similarly. There's just evaporate in air.
So why does it change underground, subsurface?
Underground it changes because hydrogen is very light. It's very light. It has a high diffusion. Carbon dioxide underground, especially in our conditions of high pressure and temperature, it can become supercritical. So how it will behave is that it will behave like a gas. It will occupy spaces like a gas, but its density is more like a liquid. It's much different than hydrogen.
So this is really promising research. Can you tell us some of the applications that you'd have in industry for this?
For sure. The application is that, as I mentioned earlier, we want to inject hydrogen underground, but we want to produce it at a later date. So we want to store hydrogen temporarily, not permanently. The reverse is true for carbon dioxide. We want to store it underground permanently. We don't want it.
Just trap it in there.
Forever. Forever. And the interesting thing is that in my study, when I compared the gases in the same pore system, I saw that carbon dioxide does not move after storage. So what I did is I've taken several images. I didn't take just one X-ray image. I've taken a second X-ray image after 24 hours. And I saw that carbon dioxide movement is very minimal. But for hydrogen, it's very fast. So why does it move in the first place? Inside the rock, I already mentioned that it's very complex. Why is it very complex? Because these void spaces are actually have different sizes. So there are some that are very small and some that are very large. So the small pores require high pressure, we call it entry pressure, to make the gas enter it. But the larger pores are easier to flow inside. They have lower entry pressure. It's like if we compare, if you go to a coffee shop and they have like a small straw and a larger straw, the larger straw, it's easier to drink
That's a good analogy.
Exactly.
Yes, I can visualize that.
Yeah, this is the same in the pore systems.
Now, Ahmed, there's something called the UAE Hydrogen Leadership Roadmap.
Yeah.
Can you tell us how this aligns with that?
Yeah. So how it aligns is we have a plan to reach net zero in the near future.
Is it achievable?
Yeah, I think so. It's achievable, but
Inshallah.
but not directly through hydrogen. I think the first step is to store carbon dioxide underground. Storing because we still rely heavily on fossil fuels. That's not, we cannot deny it. We cannot stop living without the luxuries in our life, transport, electricity, etc. So we still rely heavily on fossil fuels. And to be honest, I work in hydrogen projects, and when I compare the cost, it's very expensive. Even underground, it's still very expensive, especially when comparing hydrogen to methane. Hopefully, in the near future, the first step, which we have already done in ADNOC, is store carbon dioxide. So we can continue on it. And in hydrogen, hopefully it will be the next step.
Now, there are sustainability goals too, aren't there? There's Sustainability Goal 7. I believe that is about clean energy, yes. Sustainability Goal 9 about industry and innovation, and Sustainability Goal 13 about climate action. This looks like it aligns with all of them.
Yeah.
Tell me how.
Yeah. As I mentioned earlier, we want to reduce the climate change while also looking for solutions to clean energy. Hydrogen, as I mentioned, it's one of the solutions that we can use to make renewable energy less intermittent and more sustainable, right? The unique properties of hydrogen is that we can produce it from different sources. It's just not just renewable. We can get hydrogen from methane. So in a way, we can make whatever methane we produce clean. And the carbon that is produced from the methane, we can inject it underground.
Very neat solution.
Yeah, exactly. And yeah, the one point I forgot to mention, it's actually very, very interesting. When I mentioned the behavior of carbon dioxide underground and versus the behavior of hydrogen, the exciting thing that I saw is that, as I mentioned, carbon dioxide becomes supercritical. It's very heavy. It tends to move less. While for hydrogen, it's the other way around. It moves very quickly. And what it does is that hydrogen tends to migrate to the larger spaces from the smaller spaces. So what happens is that, as I mentioned earlier, whatever is stored in the larger spaces is easier to move. So this means that whatever we inject underground as hydrogen, it's easier to produce it back, because it's right, water will eventually trap some of it, but hydrogen has a high diffusion coefficient. It will migrate through the water and reconnect with itself, and then make it easier for us to produce it.
I can see your passion for this. You're getting excited about this so much.
Yeah.
And it really is exciting.
It's very exciting, yeah. And actually, the next step in my work is I looked into even longer periods of time. What happens exactly?
How long are we talking about?
So in my first case, I took just 2 days. The first case after 24 hours and then after 48 hours. Now I looked into longer durations, like 4 days. And then I injected brine to see if we produce all of this hydrogen from the rock. It will be filled with brine, and some of the gas, some of the hydrogen is still trapped inside. So I wanted to see if this trapped hydrogen will reconnect, and then maybe I can produce it again. And I'm still analyzing it, so look forward to it.
So watch this space. I think maybe you'll be back here to tell us about what will be next.
Yeah, it's really exciting. And from initial images, I can see that some of the gas actually have been produced, but I still need to analyze it further. The issue with the analysis of X-ray images, it actually takes a long time. It's a whole process, and I shared some of the images. Maybe you can show them now. It takes, first we need to, it's very noisy. We need to eliminate the noise.
How noisy?
It's like, we can see, like we call it salt and pepper. We can see some dots, white and black dots. So we have specialized software to deal with these images. So it will remove all the noises. And then I'm talking about a resolution of like 3 micrometer. So you can imagine it's very, very small inside this small rock.
It is indeed.
Yeah. And after we apply the filter, we try to merge, because sometimes we cannot take a scan of the whole rock. We take segments, like the top and then the middle and then the bottom. So I try to merge them. I need to make sure they are registered, because I'm injecting fluids inside the rock. It tends to move. Any very minimal movement will cause noise, and it will be very difficult to resegment them again. So these are the challenges we face, and it takes a long time to make sure they are fully aligned, fully registered, fully normalized, and then we merge them, and then we segment them, which is basically characterize from the image, which is the gas, which is the brine, and which is the rock.
You've described so many benefits. But with any subsurface technology, there's also some risk. And there's some critics of this technology, isn't there? What would you say to those critics, and how would you address the risk?
The risk, there is always risk in every project. That's undeniable. The risk with hydrogen is we always compare it, the risk with the surface storage to underground storage, as it's much safer to store it underground. But the risk underground, as I mentioned, water trapping, the gas, this is loss of energy. The other thing is that in my previous talk with KU, I talked about petroleum engineering and how it's multidisciplinary, and we also look into biology. Now I'll share why. Underground, there are some bacteria that feed on hydrogen and produce a very poisonous substance called hydrogen sulfide.
And what does that do?
It's very poisonous. It's like a small amount of hydrogen sulfide is fatal. So luckily for us in UAE, we are dealing with high pressures and temperatures that are hopefully unsuitable for bacterial growth. The other problem is hydrogen tend to cause embrittlement in metals. So when we inject underground in our wells that we already have, it can damage the wells, which can risk leakage. So we need to make sure that the design life of the well is not reliable if we are injecting hydrogen. It will reduce it significantly. So these are the risks with injecting it. But the benefit is that we don't have any contact with people, as hydrogen is very flammable. So we avoid this risk, and we avoid risk in the surface.
So the benefits outweigh the risks.
Yeah, exactly. And as I mentioned earlier, there is some risk in hydrogen leaking from the rocks. But as I mentioned, from our experience, and we know our rocks are very reliable. They have stored oil and gas for a long durations of time. Usually, what we look into is the rock quality above the storage site. The storage formation underground, we have a rock that we call a seal rock. It's a rock that does not allow any fluid to pass through it.
So it literally seals it.
It seals it, exactly. So we do evaluate it before we do any projects.
And tell me, globally, what would this mean? Are there other places in the world that have carbonate rock that could replicate your research?
For sure. The important part is that what we need to look into are the capacity of the underground formations, because when I mentioned we need, I did a calculation of how much hydrogen we need for Abu Dhabi. It's rough estimation, but it can go up to millions of tons, and taking into account the efficiency of converting electricity into hydrogen, storing it underground, and then producing it after 6 months, and reverting hydrogen back into electricity. So including all the efficiency, it's around 35%, but I'm sure it's just a rough estimation. We need millions of tons of hydrogen. So it's a huge amount of hydrogen. So we need to look into the capacity of underground formations to store this amount of gas. The other thing, as we mentioned earlier, the seal rock integrity, and the final thing is the injectivity. We need to make sure that when we inject it underground, it can take it. It's not very difficult to inject underground, because if it's difficult to inject underground, it means it will be difficult to produce it back.
Well,
In
Ahmed,
simple
you are
words.
truly an inspiring young innovator. And I'm
Thank
sure
you.
you're a wonderful role model for all our students and anyone watching, really.
Thank
And you're
you.
going to take this to wonderful places for the UAE.
Thank
you
you.
very much for coming on KU Pulse.
Thank you. It's been a pleasure.
Thank
you
you
so much.
Well, thank you for joining us on KU Pulse. And if you'd like to stay up to date on all things STEM related, then please subscribe to our channel. You can find it on YouTube, Spotify, and SoundCloud. And if you'd like to be a guest on our podcast, please contact us at ku.ac.ae/KU Pulse and submit your request. And we'll see you back here next time.